All right, let's get started.
Yeah.
I look like I've put a lot of slides in. You can't see the displayer's view, but it's maybe a little too many. But the good news in that respect is I don't normally drink caffeinated coffee, and I just had some. So we'll be able to move along quicker. However, if it gets too fast, if someone could just yell out, breathe, occasionally. If I talk too quickly, I know I have a habit of doing that. Let me see, in 1992, I grew up in Eastern Australia, which is, even though there's a lot of volcanic rocks, there's no active volcanoes, so it's sort of volcanically challenged. Anyway, in 1992, I went on a holiday to Bali in Indonesia and was lucky enough to climb this volcano, which is Gunung Agung, which had actually erupted in the early 1960s and killed several thousand people. At the time, I didn't even know that, but it was really my first introduction to really dramatic volcanic topography. At the time, I was a PhD student at the Australian National University, but I was working in the Archean, so in a very different geologic terrain, and I didn't immediately throw myself on the ground in a blinding light and dedicate my career to volcanoes at that point. But I'm sure it had an effect in moving my research in that direction. And I think it has that effect on many other people. Just to introduce myself, my name is Adam Kent. If I haven't met you, I'm sorry. Hopefully I will in the next few weeks. Although this is my last day here until the last 2 weeks, so I hope to interact with many other people then. I'm a petrologist and geochemist, so I use those tools to try and study magmatic systems. And I'm particularly interested in the interplay between magmatic processes and volcanic events, and I have projects going on in a few different places, some of them related to subduction zones, some of them not. I also run a lab, so I measure things, so as much as we try and avoid it, our research is often influenced by the toolkit we have available, and that's one of the things I do. Volcanic arcs, or the subduction zones that underlie them, we can define it as an arcuate chain of volcanoes that overlie a subduction zone, have been recognized for a long period of time. They're probably the main topographic feature that defines subduction zones, particularly subaerially. You could argue that maybe trenches are more dramatic. But it's clear from that, and it's been recognized for a long period of time, that there is a strong spatial correlation between volcanoes and subduction zones, and part of the picture of understanding subduction zones in their entirety is trying to understand the processes that lead to the formation of volcanic arcs and the magmatic systems that underlie them. So here's just a very nice example. When you get onto the continents, volcanic arcs don't look very arcy, but in the oceans they often do. This is the Mariana Arc. And so there's the various topographic features. The trench, the arc front, there's a well-developed spreading center, and then there's this older Miocene part of the frontal arc that has been rifted off by seafloor spreading. So if we think about volcanoes and we think about the magmatic systems that underlie them and the type of opportunities they allow or opportunities they provide with research, in one sense, they're to me one of the two main places where subduction zone research interacts with broader societal interests, the other being earthquakes, obviously. And so a big part of trying, or a big part of the underpinning of trying to understand volcanic and magmatic activity on arcs is to try and link to the various issues which are important to human society. Volcanic hazards is an obvious one, but perhaps equally important is that almost all the copper, for instance, that powers our industrial society comes from porphyry copper deposits, which formed in subduction zones and volcanic arcs. Then there are other issues related to environmental health and climate. If we move more into research, the sort of stuff that many of us are interested in, there are also important insights we get into things like volcanic processes, magmatic processes, crustal structure. But also because, volcanoes are really a gift to geochemists, because they take stuff that was produced deep in the earth and they bring it to the surface where we can put it in our mass spectrometers. So they beyond these sort of societal and crustal scale issues, they also give us a way to look at really deep fundamental geological questions, such as the formation of the continental crust, long-term evolution of the mantle and the deep earth. So, really we get insight to a lot of different problems by looking at volcanic arcs. And I'm going to keep saying volcanic, and if someone here is more of a plutonic person, which means, you know, magmas that didn't get to the surface but got stuck somewhere in the crust, I apologize. I didn't really get too much into the plutonic story here. I'll get to it a little bit, but when I say volcanic, I just mean all the magmatic rocks that are produced in subduction zones. And so volcanic rocks also give us a way to link different types of subduction zone research. Particularly, if we look at young volcanism, they give us a way to link with the geophysical snapshot we get of the current state of the Earth as it is now. But because rocks also go back in time and we can date them, we can also try and link those snapshots with sort of the deeper geological history. And Brandon showed some great forward modeling to try and do similar things. In many cases, those models can be sort of pegged to or calibrated in some way, and calibrated in a very loose sense, to using the geologic record, of which volcanic rocks in arcs are a big part. So for this talk, after consultation with Christy, this is you know, we've seen lots of cartoons of subduction zones, and this is one of my favorites, a paper by Bob Stern back in the early 2000s. And from seeing the list, Bob is going to be here at some point, which is great because he probably knows more about, he's probably forgotten more about arcs than I know. It's sort of, you have to be humble when you talk to Bob. Not because he's a nice guy, but it's just clear he knows a lot. It's incredible. Anyway, so this is his cartoon. I'm not going to go through the details. So the point to make here is that I'm really just going to focus on this part, what I call the upper plate. So the upper crust that melts from the mantle, pass through on the way to the surface. Later, I think next week, Christy is going to talk about what happens in the mantle, so I'm going to largely avoid that, with one exception. And then just to sort of remind ourselves of the type of information we get from volcanic rocks and magmatic rocks. You know, we can get information over a very dramatic range of spatial scales, going from sort of volcanic provinces. This might be the whole arc or a segment of an individual arc. And then I'm not going to go through this in detail, but we can also get really valuable information by looking at the submicron or the micron domain in individual crystals. And to paraphrase Sorby, who I think in 1858 published the first paper that really described melt inclusions and flue inclusions. So melt inclusions are little bubbles of melt that are trapped in crystals that are very useful for reasons that I'll go into in a little bit. He basically said something like, I can't remember the exact words, but the size of something is really doesn't scale with its importance as a fact. So we can take inferences from very small domains and make, you know, important inferences about the way that volcanic systems work. But the study of volcanic rocks in arcs does cover a range of spatial scales, and just because I think, was it Doug or Jeff said this in their talk, sort of the scales that they feel like seismic studies get to. You know, there is overlap here, but certainly we are getting information from much smaller scales because we can put our hands on samples than we get using geophysics. And is that good, bad? I don't know. I just put it up there.
Yeah, we don't do thin sections much.
That would be cool. All right, the upper plate. So this is sort of a texty. I try to avoid text in this talk because it never really gets me very far, but these are just sort of some central thoughts. Okay, the upper plate is important because that's where we get transformation from what is essentially an engine powered by mantle melting. We get the transformation of the array of magmas that are produced by that mantle melting, and there's different types that can happen, to a much broader array of the range of magma compositions that you see in arcs. And I have an example of this in a little bit. In particular, I'm sort of scooping myself here, but I want to emphasize that volcanic arcs are the home of these things called intermediate and evolved magma compositions. I'll explain what that is, but let's just get those words starting to go in there. And also, nearly all, you know, an important component of the information we get from volcanic systems are looking at crystals and the things that are inside them, and nearly all those form in the upper plate. So most of the information we get from those tells us about upper plate processes. It's a place where magma resides, sometimes for a very long time, sometimes infinitely if it doesn't make it infinitely long, it doesn't make it at the surface. But it's a place of magma resonance. So lots of stuff happens to magmas within the crust as part of this resonance. And of course, Paul, I know later, Paul Wallace is going to talk about volatiles, and so a big part of this, you know, you go from 30 kilometre thicker, or 30 or 40 kilometres, maybe even thicker. The pressure is equivalent to that at the base of the crust to essentially atmospheric pressure. Lots of the elements which are volatile, which would prefer to be a gas at atmospheric pressure, are lost. And so there's a big part of this story associated with degassing and loss of volatiles to the atmosphere, which can be important, and also to hydrothermal systems. And finally, you know, I like to think, I'm not sure, maybe I could buy a fight on this, but I also like to think that the upper plate, the crust, is sort of acting as a modulator in this whole system. And this, actually, this is an original thought, very few of mine are. I took this from a paper by, a recent paper, a science review paper by Kathy Cashman and others from Bristol. And they made the emphasis that, you know, when we go from plate tectonics, which is driving subduction ultimately, so the rates of plate tectonics are sort of germane to what is driving plate tectonics. Then we go to what can be an extremely episodic and discontinuous volcanic record. There's sort of a modulation of signal here, and I think the upper plate plays a big role in that. It also, it's not only sort of it's a spatial modulation, a temporal modulation, and also a modulation in composition. In my endeavour to introduce new cartoons of subduction zones to this group, I took this one from actually a paper I really like by a guy, Jeremy Richards, who actually was, strangely enough, was my office mate when I was at ANU finishing, just starting my PhD, and he was finishing. I didn't really like Jeremy then, because he knew a lot and I didn't. It was, and actually he still does, but I like him now, so it's okay. And he's an economic geologist, but he deals mainly with mineral deposits that form in subduction zone. And this is from a great review paper of his from 2011 in economic geology. And it's his cartoon of a subduction zone. And I am actually going to try and, I've used some self-discipline, which is rare. I'm going to try and stick to this cartoon to illustrate the talk. And basically, with some detour, we're going to start at the bottom here and just journey upwards till we get to the surface. That's sort of the underlying organization here. And to kind of even go beyond that, I'm going to talk about three main regions. I'm going to talk, well, actually, I'm going to mention the mantle. I'm not going to talk about it. I'm just going to bravely let Christy deal with that. I'm going to primarily focus on processes that are occurring in the lower crust and those that are occurring in the shallow crust. And I like to think of these in terms of sort of a metaphor of a factory, because the raw materials for this factory are coming in from the mantle wedge. They're being sort of turned into like the struts and the trusses and all those things you might use to build a big structure on the factory floor. And I see most of that occurring in the lower crust. And then finally that stuff is assembled and thrown out of the factory. And that's mainly the role of the shallow crust. The other thing I did, I kind of gave a not dissimilar talk a few weeks ago, and what worked very well was to try and insert a quiz into the talk as I went. So this is not a quiz that has a right answer. It's not a quiz I'm actually going to tell you the answer. It's just sort of an informal survey of opinions as we move forward about some interesting questions. So the first one is, what type of magmas most define subduction zone magnetism? And this actually could be, what do you call those, ink blot tests? This could be, you know, an ink blot test of your own Rorschach. I'm not sure I'm pronouncing that very well. You know, if you see an elephant in that, or a dinosaur or something. Anyway, so hands up, who thinks that mafic, and I apologize if you don't know what this term mafic, primitive, intermediate, evolved means. I have a slide in just a little bit say that, but maybe that gives me an idea of who doesn't. So who's not sure what those terms mean? All right, good, okay. That's good. I can cut out about 50 slides. So who thinks that mafic primitive magmas define subduction zone magnetism?
Does this include intrusives?
This is up to you how you want to interpret this question.
How are you using the word define?
Well... Okay. If I say, everyone shut their eyes, if I say subduction zone to you, what's the first, subduction zone magma, what's the first word that comes into your mind? All right? Okay, so if mafic magmas came into your brain straight away, I think we covered that, no one put their hand up. What about intermediate magmas? Well, this is, okay, you guys know all the answers. Evolved magmas. All right, yeah, you know, I would not debate with that. So,
What about for all of the above?
perfectly valid, Peter, I would expect nothing less from you. This is a diagram. You know, this is the sort of thing, actually, I've become the thing I hate in that respect. I downloaded a bunch of data and plotted it up on a bivariate plot. And this is exactly the sort of plot I would hound my student if they bought me this, because it's a terrible plot, right? Why is this a terrible plot? It just, you know, it gives you no idea of the density of data at an individual point. When you start plotting point upon point upon point, you know, so you lose that. However, it illustrates my point, which is that one characteristic of arc volcanism is it's the sort of tectonomagmatic environment on Earth which produces the most diverse array of compositions. That's even more evident if we just plug on a box. I didn't put symbols here, but if we put mid-ocean ridge basalts, the most productive magmatic environment on Earth, nearly all, you know, 95+% of those would plot within this box. Whereas here, if we look, this data just comes from two arcs I've chosen, the Andes, the continental arc, and the Lesser Antilles, an island arc. And we can see some interesting differences between those, but the take-home message is a very broad array of magmas are produced, particularly when we consider mid-ocean ridge basalts. You know, and I thought I'd just take a little bit of time to describe that diagram that I just showed. It had some black lines on it, and the reason is this is a diagram used a lot by petrologists as sort of a shorthand way to look at volcanic rock compositions. It just plots total alkali elements. These are elements that really would prefer to stay in a liquid under most situations versus silica, which is a great process sort of variable type thing for looking at magmas, because not only does it change a lot during magmatic differentiation, but other important physical properties, things like viscosity and density, sort of roughly scale with silica. So, you know, you can get quite an insight into a rock if you just say, what's its silica content, without knowing anything else. And it's also the most abundant element. Just to remind you, geochemists, for sort of weird historical reasons, don't like to talk about individual elements. They combine the cations with oxygen. The most abundant element in any rock is oxygen, but we sort of get away from that and don't talk about it by itself much. We just couple it with the cation, so we talk about silicon oxide and sodium potassium oxide. An interesting thing, a useful feature of this diagram is that if you melt a mantle and you produce what are called primary basalts or rocks that are in equilibrium, demonstrably in equilibrium with a mantle assemblage, they'll mostly plot in this area. And variation in this vertical axis, this is shown by the arrow here, that's mainly due to things that would occur at the source, like differences in the degree of melting, differences in the composition of the stuff you're melting. So this axis kind of tells you something about the nature of melting at the primitive end. And from that, if you then cause that whatever magma you produce that lies in that green circle to undergo differentiation, which primarily means separation of crystals and liquid. There are other mechanisms to do that, but probably that's the most important. That means you make a crystal that's a different composition to the bulk. You somehow separate that from the liquid. The liquid has to change composition as a result. And so you depending on where you start, you tend to drive on sort of positively sloped trends that don't intersect. So pretty much once you start with a rock anywhere in this green circle and start to differentiate it, its trend is going to be unique. You can't really do much to it to push it off that trend. So if I come up with something like a dacite out here, I could reasonably infer that its parent had relatively low sodium potassium with respect to, say, some weird alkaline evolved rock that occurred up here. So that's that diagram, the total alkali silica diagram. You see a lot of places if you're looking in the volcanic literature. And then everyone said they knew this, but I also just threw together, you know, mafic is relatively low silica, intermediate is intermediate amounts of silica, and then felsic. Of course, why use one word when three would work? So that either mafic, basic, or primitive would be broadly synonymous there. But, you know, none of us are guilt-free in that respect. And so again, the take-home point is that there's a big array of compositions produced in volcanic arcs. So, you know, step one for us as petrologists and geochemists is to try and explain why this is so. Of course, as I said, that's a horrible diagram, so I also threw in a histogram, so broadly equivalent, but instead just showing the silica content. I'm calling it silica because that's the oxide. If I was to say silicon, that would be the element, so silica implies the oxide. And this histogram is in terms of number of analyses, and so there is a problem because people tend to analyze some rocks, some locations more than others. But in general, the trend is such that the yellow field I want you to focus on is sort of the field of whole rock compositions from subduction zones. And again, this intermediate region is where we have a lot of samples that are present. I'm not really going to push it, but it's been known for a long period of time, and again and again and again, there's a similarity between this is intermediate compositions and the bulk continental crust. So many models for continental crust formation and evolution involve the magmas that are produced within subduction zones. Of course, the most abundant magmas produced in subduction zones are probably more primitive, more mafic than the continental crust, and there's ways to resolve that. And finally, basically saying the same thing 3 times, that I wanted to include this because volumes are extremely valuable for understanding these processes, understanding the volumes of magmas evolve, whether on an individual volcano scale or a bulk scale. They're one of the hardest things to know as well. So we don't have great volume data, I would say, for many arcs, and particularly as you go back in time, because the nature of erosion and things like that is to remove the record of eruption. So volume data is useful, but always the most sketchy. This is some volume estimates of compositions from the Cascades that I sort of made following from this sort of great tome by Wes Hildreth that describes the Cascades. Again, if we look at all Cascade magmas, intermediate rocks are about 30-odd%. Cascades are sort of unique in having a lot of mafic magmas present. If we sort of subtract that out by looking at only the main big central volcanoes, most of the basaltic magmatism is sort of dispersed around that. Intermediate magmas really dominate those central volcanoes, and the more evolved things are present, but relatively lower. So that's one characteristic of subduction zones, lots of intermediate and to some extent evolved magmas. The other thing is we're dealing with water-rich magmas in many cases here. This has, let me see, the importance of water in arc magmagenesis has been known for a long period of time, mainly through things like the presence of hydrous phases like amphibole that we saw in our rock lab yesterday. But really getting hard data on this took a little longer, and it's probably only in the last 20 years through the efforts of people like Paul, who has done a lot of this type of work. Paul Wallace over there, wave your hand for people who haven't met Paul, that's Paul. Looking at melt inclusions, just little bubbles of magma that are trapped in crystals. Because they're trapped in crystals, the volatile elements in them are sort of protected from loss when you get to shallow pressures, such as, when you get magma to shallow pressures, volatile elements want to be out, and that's what causes, to some extent, causes eruptions, like big explosive eruptions like Mount St. Helens. So if we look at melt inclusions, actually an interesting secondary question, this is from a paper by Terry Plank that some of the people in the audience were on as well, that show that most arc volcanoes, or most arc magmas have water contents that are in the sort of a 3 to 5 weight%, and that's much more than mid-ocean ridge basalt. So a mid-ocean ridge basalt varies, but would be certainly less than half a weight%. So they're wet. The other characteristic feature, I sort of harped on this already, but the presence of intermediate magmas. We saw this one, which is, has anyone ever skied at Mount Hood Meadows? All right, if you had, I know someone had because I was talking to them. Yeah, there we go. This is from Chair 26. It's a typical crystal-rich arc andesite. It has some unusual features here which are evidence of disequilibrium we'll get back into. If you looked at that in thin section, either seismically or just using your eyes, you would see it's dominated by crystals. This black-white crystal here is the mineral plagioclase. It's what all these white specks are. Unfortunately, this is not a great photo, but then you would also see other things like amphibole and that. And that's a fairly typical arc andesite, although the variance is quite high, so you can find things that look a lot. And of course, we have the presence of amphibole, which is an estimate of, which tells us that we're fairly hydrated. Okay, so you need about 3 to 4 weight% water present to stabilize amphibole. So andesites, it turns out, obviously named after the Andes, so named after a continental arc system, a big one, and have long been realized as sort of characteristic of subduction zones. And way back in the early 19th century, there was this concept of the andesite line, which is basically, it was recognized that andesitic magmas occur in relatively thin lines around the Circum-Pacific, which now we know that because that's where the subduction zones are. So that was the observation. Explaining it at that time in sort of a pre-plate tectonic context required some models that, looking back on them now, as John Eiler said in this review, look pretty non-physical, but it basically involved things like geosynclines. And I sort of did my undergraduate right at the tail. You know, the people who taught me had learned geosynclines, and I never really got it, but you know, something like the crust goes down and it comes back up and then it goes back down and comes back up. I mean, it was basically people trying to explain the observations of plate tectonics without understanding. And so in hindsight, I sound very glib saying that, but that was what people were trying to fit their observations into. Of course, oh good, you didn't get that. Just hang on a bit. Okay, I like Peter's idea of putting up pictures of people and asking who they are. So does anyone know, any student know who that is? Bowen, all right, so this is Norman Bowen. He was kind of the father of experimental petrology, and he made one of the, in this same period in the late 1920s, he made one of the key insights that he showed that andesite could be produced by differentiation from a basalt. And by differentiation, I mean forming some crystals, separating that from the liquid. The crystals would have less silica, there'd be olivine and minerals like that, pyroxene. They have lower silica than the bulk composition, so by removing them, you drive the rest to higher silica and you can produce an andesite. If we then move on to sort of the pre-plate tectonic era, it was starting to be realized that, now I don't know how to say this at all, I'm going to call it the Wadati-Benioff zone. I hope that's okay. But there were links, recognized there were links between this and between the andesite line and also between the metamorphic belts that also parallel these two features. So people were moving towards more of a plate tectonic continental margin type explanation. And also some really key, more key petrologic insights came that you could produce mafic magma by melting mantle peridotite, so that was one good way to produce basalt. And also that if you added water to that system, you dramatically lowered the melting point. So basically this is the flux melting that Christy was talking about. All right, so does anyone know who that is? Who are the two people who are from ANU? Oh, that's bad. Ringwood, all right. So this was Ted Ringwood. He was an Australian. I'm not putting him up there just because of that. But he made some, after the advent of plate tectonics, people were thinking, okay, well now we have a paradigm to try and understand the andesite line and things like that. So he advanced the idea that it was melting within the downgoing slab, melting of eclogite and hydrated eclogite in particular, that could produce subduction zone magmas. And actually, the idea is, this thinking has moved on a little bit, but the idea that melting within the slab can produce some components of arc magmas is still with us. And are you going to talk? Okay, so Paul's going to talk about some research he's done. It's sort of come and gone with the years, but I think most people are pretty comfortable with the idea that in some cases the slab melts, but perhaps not to explain all of the arc magmatism that we see. He was actually, Ted was, when I first started my PhD, he was president at ANU. Unfortunately, like many people we're talking about, he died relatively young. And at ANU, they had this great institution called Morning Tea, which you would walk into. You could get like a sandwich and a nice cup of tea from this lady called Rosa. And you would take your little sandwiches in, and then you would all sit in circles and talk about it. And occasionally, poor Ted would get stuck next to like a graduate student like me, and we'd have a conversation. And that was amazing. And when I actually got to Caltech, I was really shocked that they didn't do tea. I tried to institute it, but it didn't work. It didn't hold. Yeah, coffee would be fine. The only thing about ANU, I don't know what it's like now, but the coffee then was undrinkable. Yeah.
We bought an espresso machine.
Yeah, you know, in the early 90s, that hadn't reached the Research School of Earth Sciences, it turned out. All right, so here we go. This is what I kind of, using my factory metaphor, calling raw materials. And for all intents and purposes, I'm treating that as this. It's a black box. It's a black box that's going to supply heat and mass in the terms of primitive magmas to the base of the crust. Having said that, I cracked the black box open a little bit because when Christy was talking, there was a great question from the audience about how much sediment do we know gets into subduction zone magmas? And if I'd been more awake, I would have jumped up and said, oh, there's this great data set of beryllium-10 data, which is, to me, is one of the most elegant set of data we have, and they're quite old. They're almost, 20, 30 years old. So I'm briefly going to run through that, then I'm going to more or less abandon the mantle. And so this was work done by Julie Morris, I think at Carnegie, right? Yeah. I asked him because that's where he's from. Sorry, Peter. No. Bowen, Julie Morris, Peter Van Keegen. I can see the line going straight through.
In that order.
No, I didn't. I'm not going to tell you the sign of the slope, though. The really interesting thing about this is beryllium-10, which is a cosmogenic nuclide. So it's produced by, I don't know the reaction actually, but it's produced by cosmic rays. And then via erosion and sedimentation, it's in the ocean. So this is high in oceanic sediments, relatively high, detectable. By high, I mean the concentrations are very low, but you can still measure it. And so the vertical axis is just the amount of beryllium-10, so the cosmogenic versus total beryllium. The horizontal axis is boron over beryllium ratio. I know this looks sort of like some weird geochemical ratio. These are just two elements that behave pretty similarly when you melt, but boron is really fluid mobile. So if you go out far right on this axis, you're in sort of an area where you'd be dealing with the fluid, or the nature of that fluid becoming increasingly unclear. But you're in sort of a regime where you're transported by fluid. But the real beauty about beryllium-10 is that because it decays, it has a half-life, I think, of something like 1.6 million years. Does anyone know? Anyway, and so a rule of thumb, radioactive decay, you have some radioactive element, you wait 5 to 7 half-lives, it's undetectable. So that gives us about 10 million years. So what this means is that we can go to arcs, we can pull up rocks that erupted yesterday or in the last few thousand years. If we see beryllium-10, it's incontrovertible evidence that oceanic sediments have gone down the subduction zone, have been incorporated into those magmas, and it's all happened within 10 million years. So the interesting thing is, and maybe someone here, let's not get into it, but this is quite old. I wonder whether this is something that some hungry young geochemist could revisit, even in a simple way, perhaps as part of a CIDA workshop, by instead of revisiting this, but using the partitioning related to supercritical fluids rather than sediments, and see whether that might be an interesting afternoon's work to see whether that changes the story. The array here of different arcs just tells you that there are different amounts of sediment versus fluid being added. And then just to quickly answer that question that someone asked, generally when you sort of invert arc magma compositions for how much of a subduction component, be it either fluid or sediment involved, it's a few percent. But somewhere between 1 and 5%, something like that. So it's not a lot. All right, next quiz question. Where do we produce most intermediate and evolved magmas? The upper crust, the lower crust, or the mantle? All right, so who thinks it's in the upper crust? Oh, this group's no fun. Who thinks it's in the mantle? All right. Let's move right on. All right, so now we're going to move on to the factory floor, the lower crust. We know there is abundant evidence that the continental crust plays an important role in dictating the composition of arc magmas, whether they be plutonic or felsic. This is just one data set. Again, it's one of those horrible plots. I don't know what I was thinking because there's a million data points. But hopefully, again, versus silica, so here we go from primitive to evolved, versus the strontium 87-86 ratio. Some of you may not know that, so a very quick primer is that this ratio basically reflects the time-integrated rubidium-strontium ratio in this rock. Rubidium is more abundant in the continental crust. It has a higher rubidium-strontium ratio, so through time, continental rocks evolve high values of strontium 87-86 ratio. And that's exactly what we see, particularly in the Andes, because you've got thick, old crust there. So you're quite sensitive to addition of strontium from the continental crust. So this is interpreted as incorporating elements of the continental crust into these magmas as they evolve. It's a little more subtle in the cascades because we're dealing with primitive, younger crust, so it doesn't have very different strontium isotopes. But if I was to show you the same figure in oxygen, for instance, you would be convinced of that. having said that, so stepping back into the history line a little bit, and to finish that up, so after Ringwood and Dave Green and other people really pushed the role of melting the slab, there were sort of diverse schools of thought for following that for probably a decade or more, sort of trying to think about the role of the crust versus the role of the mantle in producing this big diversity of arc magmas that we see. And you know, I wasn't really in the game then, but my feeling from looking back that if you'd taken the position that nearly all the diversity in arc magmas was the product of mantle processes, you would have had allies in that. I don't know, what do you think? I mean, is that was a sort of an extreme end of the point of view, but I think that was, people had that.
Yeah, I think people had that. I mean, it was about this time that Planck and Langdon came out and showed the differences right now. This was about
The same time Planck's PhD work was published.
Yeah. So sort of towards the late 1980s, a number of papers came out, which including this one that I'm highlighting because it has been very influential, by Wes Hildreth and Stephen Morbarth, which was sort of a very detailed study of a range of volcanoes from Chile. And they're interested in this question of the role of the upper crust, and particularly the role of the lower part, the role of the crust and the role of the lower continental crust. And they took advantage of a natural experiment, which, as we all know in geology, finding a natural experiment where you can kind of control several variables is pretty hard. So kudos to them for recognizing this and coming up with what I think was a very influential paper, and it continues to be very influential. Okay, so here's the trench along this latitudinal section, which I know this is small, goes from about 30, I can't even read it. So I think it's about 38 degrees south to 33 degrees south, something like that. Things like convergence rate, convergence direction, other kind of slab parameters, subduction parameters don't really change much. The main thing that changes is the thickness of the continental crust, going from about 35 kilometers to the south and then thickening dramatically to about 65 as you go north. So of course the mantle wedge changes a little bit because that's geometry sort of requires that. But the main difference here is going from a reasonably thin crust to something that is quite dramatically thicker. And so I'm going to cut to the chase. If you go along those latitudes, so 39 to 33, and these initials just refer to all the individual volcanoes, there are dramatic changes in the composition of the rocks that are erupted from those volcanoes. And I'm just going to highlight two. One is the strontium 87-86 ratio increases very dramatically. So you could interpret this as saying that the role of the continental crust and the amount of incorporation of continental crust increases very dramatically as you get to this region of thicker crust. So this is sort of, here is the demarcation between the thinner and thicker crust. There's sort of a transition at this point between 36 to 34. And the composition of river sediments from both these places are shown in purple, and so it's clear that the change in strontium 87-86 could be in part explained by composition of the crust itself and or addition of increasing amounts of continent or incorporation of increasing amounts of continental crust. However, the real insight to that is when you look at the involvement of garnet. So the rocks in the lower crust that we are melting or that are available for melting are amphibolite, so sort of the metamorphic equivalent of basalt. And about 35 kilometers in an amphibolite in the continental crust, garnet becomes stable. So geochemists love garnet because it has a very recognizable effect on a number of elements, particularly the rare earth elements. So I just have shown here a ratio of 2 rare earth elements. If you don't know about the rare earth elements, it's no big deal. Just remember that this one, cerium, a light rare earth element, doesn't really care for garnet. Garnet's there, it doesn't mind, it's like, I'm okay, I don't need garnet. Ytterbium, on the other hand, really likes garnet, okay? So if you melt, produce a magma, and you leave garnet behind, that magma will have low ytterbium because a lot of it stays behind in that garnet phase. So in a way, we have by looking at this ratio, if it's high, we have garnet involved because that means the ytterbium is low. If it's low, we don't have garnet involved. This is like a very simple way to look at the pressure of where those magmas come from. So cut to the chase, if we get to thick crust here, we see a high garnet signature. It means that we have to be incorporating elements from the lower crust into these magmas. Everyone good with that?
So the dots mean high cerium ytterbium?
The dots there? The dots are, sorry, I just put those to highlight. They are the strontium 87, 86 values of local sediment sources, like average crust.
Oh, so this
They're nothing to do with this
doesn't
serum
actually
turbine.
show the serum.
It does not actually show it. It's only in a very quantitative way. Yep.
Adam, just
Yes.
quickly, are those basalt and andesite or mostly intermediate?
Mostly intermediate, yeah, or too evolved, yeah. There's not many basalts, thick crust. In fact, I don't know if there are any basalts on that section, that part of that segment. All right, so the idea that Hildreth and Morbarth advanced is that you have magmas that are coming off the mantle, they're coming into the lower crust and they're stalling. And so why are they stalling? Perhaps because they hit some type of density barrier, meaning the lower crust, a change in density, so they kind of get trapped in there. Perhaps there are other permeability or viscosity reasons for that. But you start to build up sort of what is often called a plexus, a sort of a region where you get continued intrusion of hot basaltic magmas into the lower crust. And actually, if you look at crustal sections, you can see areas that look like this. This is just an example from what is called the Famitinian arc, which has been worked on by B.J. Walker, who working with George Bergans in Argentina. This is an Ordovician cross-section of a volcanic arc that's been turned on its side, so it's perfect like that. They mapped it out, and there's a section that goes from somewhere like 30 kilometers, if you look at the pressures, to 14 kilometers, showing this area, which is interpreted as sort of this region, this plexus of lots of intrusion, relatively mafic rocks, and then becoming progressively more silicic as you move up crust. This is more or less, my understanding, is consistent with seismic velocities within the crust today, so relatively primitive rocks at the base and then sort of refining upwards into more evolved. Was there a question? I thought I saw a question at the back. No, okay. All right, so you're intruding this sort of plexus of dikes and you create what Hildreth described as a mash zone, subsequently described as a hot zone. This is a region of very active magma formation. If you're intruding dikes fast enough, you're able to elevate the temperature of the surrounding crust enough to start to melt it. And I'll go through this in a little more detail. Actually, I have a slide right here. Okay, so you're intruding this sort of plexus of dikes. In this case, it's sills. Some people do it as randomly oriented sills. Some people do it as a randomly oriented dikes. Some people do it as a plexus of sills. The idea is that we're talking about a flux. We're talking about adding magma fast enough to the lower crust to maintain elevated temperatures such that both the surrounding rocks start to melt. So the surrounding rocks are going up temperature, so they're starting to melt. The intruded rocks are going down temperature, so they're producing more evolved melts as a result. They're crystallizing, producing more evolved rocks. That whole mass of produced melts can then mix together and produce a bunch of more evolved magmas. So let's just have a look at that in a little more detail. So this is the idea if you took a basalt parent and started to cool it within one of these zones. And along the bottom, unfortunately, this is from a paper by Joe Dufek and George Bergans. It's not temperature, but you can take this as temperature if you like. And also increasing silica content in this melt fraction. So you start with a pretty high, you would intrude a magma, mostly as melt in this case. It would start to cool, crystallize out all these species, and you're left with some amount of residual liquid that has a more evolved composition. So that's what the surrounding rocks are doing. That's their down temperature path. Sorry, that's the intruded rocks. That's their down temperature path. At the same time, I think I'll just skip this slide because I have a lot. At the same time, the surrounding amphibolite rocks are increasing. Mostly people have used amphibolite for these models with the understanding that you're dealing with a fairly mafic lower crust, although you can use greywacke or some other starting lithology, and it sort of works as well. It's experiencing an up temperature, so again, temperature goes from left to right. As melt fraction increases, you are producing a melt of amphibolite. And again, as you're doing this, you're producing liquids that have higher silica contents than the basalts you started with. So those are two sources of liquid that you can produce, and then it can mix and blend together to produce a range of intermediate and evolved compositions. So the interesting thing about this is that it's related to flux, right? You have to be adding magma fast enough to maintain elevated temperatures. So if you were to do this process but just add you know, a sill every million years, nothing would change, right? Because that sill would retreat into relatively cool rocks. The sill would quench or whatever, would cool down, crystallize, become solid. And most of that heat would dissipate prior to the next sill coming in. So you have to be doing it pretty fast. So this is flux on the bottom axis, so high fluxes versus depth. So to cut the story short, basically this is a very good way to produce evolved and intermediate and even evolved magmas, but you have to do it in relatively hot conditions of the lower crust. If you do this in the shallow crust, where ambient wall rocks are much lower temperature, you really can't get significant magma formation at reasonable kind of flux rates. That's sort of the take-home message from that. And that's what this plot shows. You know, this is degree of melting, and it decreases as you go to lower fluxes, so less sort of heat added per unit time, and also go to shallower pressures. If you do the same thing looking at that amphibolite dehydration, the same thing happens as you go to shallower crustal pressures and or lower fluxes. You reach a point where you melt very little or not at all. And I didn't show the bottom panel on the previous figure, but I'll just show it here. This is the same axes, but it's sort of showing the silica content of that dehydration melt of amphibolite. So if you do it to a pretty high degree, you get something intermediate, maybe even more mafic, and then if you do it to a low degree. So you can produce a range of evolved compositions here. I think I'll skip that one, unless we have questions, I'll come back to it. Okay, so those two, you know, you have a number of ways to produce, let me just, somehow I must have deleted it. Hildreth called this zone the mash zone. So thought I had what it was there. It stands for melting, assimilation, storage, and homogenization. So it's a very active zone. You're having melts produced by at least two different ways. They're mixing together. They're producing sort of volumes of magma that are then capable somehow of rising out of the lower crust into the shallow crust. A subsequent paper, actually they came around about the same time as this Dufek and Bergan's paper by Catherine Annan from Bristol with John Blundy and Steve Sparks, called this the hot zone. So you can call it the hot zone, you can call it the mash zone, it doesn't really matter, but it is a very important region for trying to understand arc magma formation. So beyond that, we are now moving up into the shallow crust, what I've termed assembly, and there is really excellent widespread evidence that most volcanoes, or at least nearly all volcanoes, arc volcanoes, other volcanoes, are underlain by a region of shallow magma storage. And so a number of ways you can look at this, but this is a great histogram I produced from data from this paper, just showing depth of magma storage inferred by various geophysical means, you know, like deformation, seismic tomography, other ways. And it shows that there is sort of a mode of storage between 5 plus or minus 2 kilometers beneath the volcano, and all sorts of petrological, whether you use mineral barometry or melt inclusion saturation pressures, get you there as well. So I think that there's almost incontrovertible evidence that there's very widespread storage of magma underneath volcanoes, which sort of makes sense. You know, that's where magma is staging to get ready for eruption. A part of that, a dirty little secret, is we actually don't fully understand why that's the case. So this is not so much a quiz as a survey. So why does so much magma resonance occur in the shallow crust? So could it be trapping of magma at the brittle ductile transition? Stalling of ascending magmas? All right, well, this density, viscosity? We have a mass balance problem here. Yeah, that actually is a very interesting question. I think it's pretty good reason to think that stalling of ascending magmas associated with viscosity is one important mechanism, but there have been several review papers of what we don't understand about volcanoes in the last few years that really highlight what it is that causes magma to stall in the shallow crust, say of just going straight through and erupting. An interesting fact is that estimates of the amount of magma in a magmatic system beneath a volcano that actually erupt are pretty small, like 3 to 30%, sort of the range of estimates that people have. So actually most magma doesn't make it out. So we'll look at this in a little bit, but another important thing is that for those of us who like to use mineral compositions of sources of information, nearly all minerals probably form within the shallow crust, or a large proportion of minerals. So these are plagioclase crystals. This is from Mount Pinatubo. Obviously, it's been fractured by this is from a pumice, so it experienced sort of an energetic phase and got fractured. But the range in grayscale reflects chemical composition, and mainly the calcium content versus the sodium content. So we can interpret this, these variations relate to mixing of magmas or changes in pressure and temperature or something like that. So it's a very rich information source, almost too rich sometimes because it can be a little non-unique. Same thing, this is a plagioclase from Mount Hood, which shows sort of stunning oscillatory zoning, exactly the same thing in the abundance of calcium with respect to sodium. A lot of information stored in these crystals. Most of those crystals probably stored at pretty shallow depths, and the reasoning behind my saying this also perhaps gives us an insight into how the way that, or the reason why magma stalls as they reach a shallow crust. So this is a phase diagram. It's from this paper by Annan et al., another very influential paper on sort of the formation and behavior of intermediate magmas in the crust and subduction zones. So showing pressure, showing temperature, shows the liquidus for H2O saturated. So if you had a magma that was H2O saturated, it would be liquid on the right-hand side of this line, solid on the left. And then if you're not H2O saturated, because at such high pressures you need a lot of water to saturate a magma. Basically, saturation means you add so much water that you can't add any more, and if you kept adding water, you'd have a free vapor phase. If we're at the 10% water and we start sort of instantaneously with an andesitic magma at depths, this is equivalent to maybe 30-something kilometers. And if that ascends, it follows this adiabatic path, kind of like Christy showed yesterday or the day before, I can't remember. The rise path sort of deviates from the liquidus. So if this magma here is crystallizing, it's sort of straddling the liquidus here, so it could conceivably be doing that. It moves off into a portion of phase space where suddenly those crystals are unstable. What that means, if there's any sort of mineralogical record of this, either what restite, crystals sort of inherited from the source rocks or anything like that, they undergo a period of dissolution or instability. So a lot of the mineralogical record, if any, was made of this process is destroyed as this magma ascends to the crust. And eventually it doesn't actually crystallize until it gets back to the liquidus here, but then crystallization can occur pretty rapidly. So if you run the numbers like Catherine does in her paper, you can sort of stall magmas out just by going from almost no crystals to so many crystals, 50% crystals or something like that, where a magma is viscously locked up. And you can do that very quickly. So this could be one idea why the shallow crust is such an important place for magma to reside. We saw evidence for this in our rock thing, so I won't belittle it, but these shallow magma storage zones are really also a very dynamic environment, and there's very often evidence for mixing and blending of multiple magmatic components. And so this is one sort of macroscopic evidence for that. These are called quenched inclusions. These are interpreted as a chunk of another magma incorporated into this broader magma that hasn't quite been completely mixed in yet. And even if you go and look at individual crystals within this is from Mount Hood, which is a really good example of this, you find there are often two populations. And the histograms just show for amphibole often a range of different volcanoes that if you go and look at a single thin section, you find crystals that have different origins. The interpretation is that they represent blending of different magmas that happen at a pretty shallow crustal level. Let's skip that. And you can actually, I just put this in because someone asked me what does that sample we looked at in the rock lab, the really banded dacite, andesite from Mount Lassen look like in outcrop. So I found this USGS photo. This is a really great example. Clearly we're mixing two types of magmas here. We've done it incompletely. We've done it very shallowly and probably immediately before, even perhaps during eruption. All right. I think it's the final quiz. Long-lived bodies of eruptible magma are probably quite common in the shallow crust. If you don't know what eruptible magma is, that's great because that's an important point. So this is just true or false. So who thinks that's true? All right, who thinks it's false? All right, I think my participation rate is dropping. Well, you should have compulsory participation. That's how they get people to vote in Australia, They send you a fine if you don't vote. And it's like, oh, we got 90% attendance. Amazing. All right. Well, we'll get to that. Another, I emphasize the broad range of compositions in volcanic arcs. That's accompanied by a really broad range of volcanological phenomena too. Different types of volcanoes, shield volcanoes, stratovolcanoes, calderas, and also by this tremendous range of volume of material that's erupted. So this is just a thing you can find on the internet when you have 2 minutes before a lecture in introductory volcanology. And it just shows the volumes of different volcanic eruptions. Maybe you know some of them. And not all of them are subduction zone related, so Yellowstone, maybe not. This Wawa Springs, this gigantic one, it's sort of an honorary subduction, but it's not, it's related more to flat slab transition. Long Valley, I really don't know. But Toba is an honest to goodness subduction zone volcano that 70-something thousand years ago erupted almost 3,000 cubic kilometers. That's a lot of magma. And then we go to even, Mount St. Helens in 1980. It's quite famous, but it wasn't that much. And then we go to these tiny little dribbles that come out of things like Mount Hood and Mount Lassen. There's a big range of magmas, But what that means is at some point under that volcano, that volume of magma had to exist in an eruptible state. Is there any way we can get around that? I mean, there's no real way you can get around it. At some point, under that volcano at Toba, I mean, that's just insane. There's like 3,000 cubic kilometers. Accumulations of magmas have to exist like that, even if transient. If we consider what I'm saying about eruptible magmas, it's just a matter of viscosity. This is a viscosity, the blue line here, of a magma as you cool it, in terms of the mass of crystals, or viscosity, sorry, on the right axis. All it says is as you cool a magma, you have to crystallize. That's the response. And by the time you get to about 50% crystals, you lock up. Some people say 40, some say 60. It doesn't really matter. So a magma that is present with more than about 50% crystals is not something you can take as is, propagate along a fracture to the surface and make it erupt. You have to do something. Well, it's sort of interesting what you have to do. So there are a couple of bells and whistles you can play. One is how quickly you inject magma from below. If you do that quickly, you can kind of create something that's, at least for a transient period of time, is quite warm. Warm equals low crystals equals relatively low viscosity, able to erupt. And you can also look at the response of the crust around it. This is a really interesting result of a really interesting set of models by Wim de Gruyter and Chris Huber, looking at the elastic response of the crust versus sort of the rate at which you add magma. And you can kind of get multiple regimes of eruption. If you add magma really quickly into an elastic crust, you've got a pretty good chance of rupturing that, getting magma to the surface. If you add it slowly, it'll tend to crystallize, but sometimes you can produce enough vapor phase to increase pressure to do it. But if you want a really big eruption, the way you have to do it is intrude magma moderately rapidly, but into a crust where the wall rocks are going to be able to deform to absorb that. Back to the question of how much eruptible magma is present beneath volcanoes, I think the answer is we don't really know. But at present, observations suggest not that much. And so Jeff or Doug might want to chime in, but most experiments, or Brandon, most experiments that have tried to use seismic or MT techniques to work out and look for bodies of eruptible magma underneath volcanoes have not found, they've found bodies of what some people might call magma. That means there's a melt present, which makes you sensitive to seismic velocities and to electrical conductivity. But in terms of something that actually has less than 50% crystals, I personally am not aware of any sizable body of underneath a volcano that's been recognized. Maybe someone can set me clear, but so it's a bit of a mystery because we know volcanoes must produce this stuff. We don't see it. And so that's led to a sort of a paradigm where most of the magma that exists beneath volcanoes exists in a very crystal-rich state, which sort of makes sense thermally. You're in a relatively cold environment. Any magma that you stuff into the shallow crust will cool pretty quickly until it gets to be crystal-rich. Then there's some buffering from latent heat as you approach eutectic conditions. And so most of the magma might be in these sort of crystal-rich zones that are remobilized very quickly in a very transient sense to produce something that can erupt. And I think this is pretty much my last slide, except for some fancy questions. And this is from we're now developing petrological tools which sort of let us probe this question of how hot and how long has the magma been. This is from a paper that just came out in the last few weeks. Christy and I are both involved. It's by Ali Rubin, who was a PhD student of Carrie Cooper at Davis, not too far away from here. So I'm going to go fairly quickly through it, but basically what we were able to do was to use diffusion of the element lithium, diffuses at the right rate, compared with the age of zircon crystals to work out how long a zircon crystal could have spent at a given temperature. So if we take a zircon crystal and say, okay, we want it to spend time at 750 degrees, these are the sort of time scales involved. So these numbers refer to the total lifetime of that crystal that it spent at that temperature or above. So very small amount. This actually is the temperature you need to have the magma at in order to erupt it. So, I mean, strangely, and this sort of supports some earlier work, but it kind of suggests that a crystal, and by inference the magma that contained it, spent really small amount of time at 50% or less crystals. Most of the time it's just solid. Even if you go to something that's even more weird and you go even kind of temperature like 650 degrees, that is probably below the solidus, you only spend 1% of your time. So this actually probably was a rock that spent its time almost solid and then somehow got reactivated to erupt. And modelers hate this because once you crystallize a magma completely, you drive off all the water. So it's basically non-reversible. You can't then add that water in easily to make it melt at the same temperature. So we don't really know what the answer is there, but it looks like this reinforces the idea that lots of magma spends lots of time beneath volcanoes in a relatively cold, rigid state. So that's where I have done. I think I'm okay with time. I must have spoke really quickly, but I don't feel any lack of oxygen, so I'm still able to breathe quickly enough. What I wanted to do then was just to move on to some questions that I and others have thought some interesting or big questions to solve, and perhaps some of them are tractable by this group. To start with, there's this sort of grand challenge. You know, I've tried to give you the best picture of how we understand magmatic systems in volcanic arcs to work. It's sort of mine. I'm sure other people have differences on that, but we're still lacking sort of a grand vision for how magmas form. You know, I don't know, maybe Paul, have you had this experience? You're driving with someone in the Cascades and they say, oh, you know, those volcanoes look evenly spaced. Why is that? And you go, you know, that's like a really good question, and there's some answers out there, I don't know. And then they go, but then the three sisters, there's three sisters here. There's like 3 volcanoes really close together. Why is that? I don't know. And then you go, oh, well, you know, Mount Hood's dominated by andesites, but then you go, you know, 70 kilometers north of Mount St. Helens and it has basalts through to much more valve magmas. Why is that? And you go, you know, I don't know. So we're lacking like a grand vision to link what might be happening in the mantle wedge to the lower crust, to the upper crust, that would let us explain things like the lifetime of individual volcanoes and why volcanoes are sort of occupied for 500,000 years. That's sort of a typical number for the Cascades. Most edifices are about 500,000 years old or so. But then they're abandoned, and there are plenty of abandoned volcanoes in the Cascades. They're not on this map. Why some of them are dominated by different magma types and different processes. You know, why people have summarized this as volcanoes have different personalities and they sort of change in some way as you go. And we don't have a very good grasp of why that's the case. And where the main controls are the controls on like mantle flux. Is that really an important button? Is it like the stress state or the lithology of the crust? Is that an important button? Another really cool sort of part of this, but it's really small, is sort of that the communication, and Brandon talked about this, so he stole a lot of my thunder, but he didn't show this figure, which is really cool, about how you communicate between the lower crust, where you're producing a lot of magma, and the shallow crust, where you're both storing it and staging it for eruption. And there's a really interesting paper from Soufriere Hills volcano, which erupted more or less continuously for a few decades, starting in the early 90s. And by using deformation, people are able to recognize at least 2 magma sources, one in the shallow crust and one in the lower crust. But by looking at long-term deformation records, you could see that obviously this source deflated with eruption. That makes sense. But once that stopped, this source would deflate and then this would re-inflate. So there was this sort of really interesting interplay between eruption, emptying this shallow magma chamber, and then new magma coming in and from the lower crust and or the mantle beneath. And Brandon showed this, I'll reinforce it. You see a similar thing at Mount St. Helens, that this is the seismicity record for Mount St. Helens in depth versus years. So it starts in 1987, so it doesn't show anything from eruption. In fact, the 2004 and 2008 eruption has been expunged just to make it simpler. But there are these episodes of deep recharge that are interpreted as magma from deep in the crust moving up shallowly to sort of refill or rearm the reservoirs that exist. And most recently that happened in 2016. You always get a few new Twitter friends when that happens, because you show some picture of Mount St. Helens and it's very popular. You have no idea about the interest in volcanoes in the Pacific Northwest. People really like their volcanoes. And maybe they do that everywhere else. I don't know if we could sample it. The other thing I think but is a struggle for us is to try and integrate our petrological and regional geochemical data sets with the more expansive and more integrative geophysical records. Part of this problem is geological, right? We don't get to say, go there, get a basalt. Maybe there is no basalt there. There's no there, right? So we have to try and think about new tools that we can use to produce things like the bulk properties of our volcanic record, things like just an average or variance or something like that, and then how we could maybe try and link that to broader scale geophysical data sets. Part of that problem, though, is not geological, it's of our own making, and that's because petrologists and geochemists are kind of like magpies. If they see something interesting, they'll just go and pluck at it. So this is the number of samples available out of a total of almost 8,000 along the Cascades. And you can use this to map the stratovolcanoes, like Mount St. Helens, Newbury and Three Sisters, Crater Lake, Lassen area. So, there's a factor of something like 10 difference in sample density. So if I was to calculate an average composition based on these, it would be basically Mount St. Helens. So and you can use tools to back that out. So this is sort of a bootstrapping approach that my student Brad tried. But I feel like we're scratching at the early days of that. I think there's many more ways we can try and take, and perhaps people out here who are not petrologists but have used similar approaches can provide some insight. And that is it. Questions, comments, missiles?
We're having some organizational difficulties here. Questions first for students and or postdocs for Adam.
So kind of a general question, comment, more from a seismic perspective. But one of the reasons I've thought about why we're not imaging these higher melt percentages is because the waves just don't penetrate through it. We don't have the station coverage to actually see that, and our rays will just bend away from these things because they're so incredibly slow. So, and like you said, the maximum we generally see is around 20 on non-typical volcanoes. So I'm wondering if that's kind of a max that you can have for some crystal mush and still propagate seismic waves. I don't know if the seismologists have a comment on any of that. Do you think we just can't image those high melt percentage bodies?
P waves propagate fine. P waves propagate fine in 100% melt. So, it's basically you get slow velocities, but the waves will propagate through.
But your ray path will be wrong if you use an approximation
around the body. So,
right.
Yeah. I mean, maybe Brandon wants to comment more. I don't know if he's here.
I think there are some areas where they just need to be big enough. Right? You need to be able to have a path that's going to go through the middle. People have tried to look at some odd phases. I think there's a very interesting modeling paper. I don't know if the numbers are dead on, but for for Yellowstone, Rusheng Chu has an interesting paper where he sees the polarity of waves flip if they're coming around the edge of what looks like the upper crustal magma body, at least based on gravity and based on heat flow. It's clear there's something very big there, and it's enough to completely reorient the direction of these waves. They think it might take tens of % of melt to do that, so maybe it's getting into the neighborhood. But you need something big enough, you're absolutely right, so it doesn't wrap around. I would guess maybe there's something small at Mount St. Helens, but if it's only a few kilometers wide, we're not going to see it if our source receiver path is 30 kilometers long. It's a small deflection to go around it, so that you're right that that's part of the problem.
What about MT? Is anyone here informed enough to? Oh yeah, yeah.
Yeah, we would see it. But it's the same. I think it's the same situation. It depends on your data coverage.
And what is the nature of the trade-off between like interpreting as a big body with a small amount of melt versus a small body with more melt? Is that sort of a non-uniqueness, or is that?
Yeah, it's a pretty big non-uniqueness.
Yeah.
One comment I might make is that I suspect that in many cases, what we envision as some huge, completely solid body of magma has a much more complicated geometry, and it's a pressurized system, so it communicates completely, but it's not sort of completely round and solid like we imagine it. It may be just sort of interconnected regions rather than a solid magma chamber. And I think there's some studies of like plutons and so forth that suggest that's the case.
There's also an element of transientness to it, like Mount Pinatubo, that the magma body that erupted was basically just turned on within a month or so from probably something that I'm not sure it was solid, but it was probably quite crystal rich. And so if you're not at the right place at the right time, maybe you don't see it. There are other systems where you could probably infer that the magma body would sit around for longer, but that one was, you had a month maybe to see it, maybe less actually, maybe days.
Postdocs and students, Bruce. Well, hold that thought for just a second. Huh? This is your time. I know you want to go to lunch, stand in line with all the soccer people. Wait 5 minutes for the salad bar. I found the pizza to be available all the time, and there's a reason for it, so don't follow my lead.
So you noted that only a relatively small portion of magmas make it to the surface, and is there much of an understanding why that is? Do only certain magmas make it to the surface and others don't? So is there some sort of internal control, or is it more of an external control?
Well, that's a very interesting question. So first thing to note is that if you go from sort of the extremes of composition that we see in arc magmas, you go through probably 6 orders of magnitude of viscosity, sort of depending on how many crystals you have, and like 30% density. So if there are parameters that control the mobility of magmas, they change quite dramatically. So you could imagine that you're biasing that set of rocks that make it to the top of a volcano, because some simply there's a mechanism to erupt them and some not. Having said that, so this is not just, I didn't include this because this is not just arc rocks. This is all volcanic and plutonic rocks available on planet Earth at the time of this formation of this paper. But the paper is, that histogram of abundance versus silica is corrected for differences in sampling density. So this is probably the best estimate we have. So it does show that plutonic rocks are much more dominated by silicic compositions, would be more viscous. Unfortunately, I think this also has mid-ocean ridges on it, so that might produce that peak at basalt. The paper's not super clear about exactly what goes in here. But I think probably, I'm not doing a very good answer to your question, Dan, but I think what we get at the top is probably heavily biased by what's called a filtering effect. Some compositions and some types of way you promote an eruption tend to favor samples that get to the surface and we can use and not.
Also, just to add to that, it's probably crustal like stress state.
No, but this is follow up.
I'm just adding something to the answer, which, that's right. No, Adam's answer is excellent. And one of the things that's controlling then when you have a certain density or you have a certain viscosity, it's not that there's always a certain density or viscosity that can make it to the surface. It's then on top of that crustal stress state, for example. So we see a lot more mafic magmas erupted in the southern Cascades Arc, where there's extensional processes at work, than we do in the northern Cascades Arc, where it's under compression. So the thickness of the crust and the sort of stress state of the crust are probably important in engaging that filter. So there's maybe geographic diversity in what can make it to the surface as well.
And also, you know, one thing I think that if you're trying to explain different volcanoes like this that have different personalities, the thing that varies laterally the most is the continental crust. Well, maybe not actually, maybe I would get a debate on that. So whether it's structural state or lithology or thickness or something, I think there's a very strong feedback between that and the given flux of magma coming in from the bottom, the timing of that to produce what ends up coming out the volcano.
Yeah, so I guess in my work on some of the seismic imaging of some of these bodies, we've got a lot of pushback because it seems like volcanologists like to say that the average plutonic to volcanic ratio for a volcano is 5:1. So it's, to me, that's not, it means there's quite a bit of it actually coming out to the surface, and a very small amount is actually forming plutons. Do you think that number isn't accurate?
My understanding of that number of people done, it's the other way around. So 3 to 30% get out the top and the rest stays in. And that's from, I can put you onto a paper, like the state of the art is a paper from 2005. I don't think it's been redone since then. And it might depend where you're talking about. If you're talking about like the shallow volcanic area, it might, you know, that ratio might be more like you're talking about. If you're talking about the whole crust, you know, comparing to the flux of material that comes in the bottom, the amount that eventually gets at the top. And I have to go back to this paper by White to see exactly what they have defined there. I tend to think it's more shallow crustal. So that, at least, they include that, in some cases, very small amounts get out. And that's sort of the rule rather than the exception. So I know about 5:1 volcanic to plutonic sounds really high to me.
So I'm just thinking about the magmatic addition, and if there's all of this plutonic material coming in and staying in the crust, like that's going to add a whole lot of volume over a subduction cycle. And so I'm just kind of trying to think about, you know, a lot of geodynamic models, as I understand, it's really hard to incorporate the magmatic part of the system and how that might kind of change the models, how that might affect some of the stresses going on and things like that. I don't know if you have any comment on that.
Oh, well, I'm not really informed to comment on that, but that's never stopped me much in the past. There's some great studies looking at the effect of, say, an overpressured magma reservoir or the weight of the edifice. I think that's slightly smaller scale than you're asking about. But, you know, say the weight of the edifice itself has a very dramatic effect on the local stress state and can control, you know, a big influence on magma transport, if that's by dikes, which is very dependent on the stress state. That's all I have to say.
So I was wondering whether there's an alternative thought about magma. We know there are things at the shallow depth. We see them. But how much of those are really coming to the surface? Because there is a delay between being stored there and maybe over 100,000 years later, they will erupt and we wouldn't see them. Is there an alternative thought about how much of the magma that make it up to the surface was actually made and crystallized during the ascending, or the process happened in the deep crust?
I mean, Yes, you can see evidence sometimes that magma is produced in the shallow crust by melting, like oxygen is a good one, but that's relatively rare in arcs. It's mainly sort of an extensional type or caldera volcanism thing. Certainly, you can, I think that the thermal arguments to me carry a lot of weight, so I think it's much easier to make significant bodies of magma in the lower crust, because that's just where it's much, much easier to melt amphibolite to some degree. Does that mean that you never melt shallow crustal rocks? No, I doubt it. Yeah, I'm sure that happens. You know, that would be assimilation. In fact, at Mount Hood, we see some oxygen isotope evidence for that.
Okay, well, let's open it up for the last few minutes to Senior. Paul, you're number 3. So hold on.
Sure, yeah, absolutely. You had made the comment that you needed sort of 50% melt fraction or crystal fraction to be eruptible. I wonder, are there geometric constraints as well? I mean, if the melt was distributed in sort of thin veins, could you not then get it out? So, I mean, are there other sort of geophysical or rather physical constraints that are imposed on what's required to be eruptible?
I'm sure there is. I mean, for dike transport, for instance, there's a constraint on you have to have enough going through the dike to avoid heat loss to just sealing up, like the Rubin type analysis. I'm sure geometry plays a big part. Even that 50% crystals thing is sort of rough because, you know, in detail, the viscosity of a crystal liquid suspension is super complicated as you get to that 50% point, and the shape of crystals themselves can have, you know, if they're tabular versus elongate versus equant, can have a big effect. So I'm sure you're right. I'm sure there are other considerations as well in terms of geometry.
The question really was whether you could distribute the magma in such a way to make it difficult to observe by seismic.
Well, actually, that is a great question, because there is one type of eruption, these sort of low crystallinity rhyolites, like a good example would be Bishop's Tuff, that look, I mean, one model for those is that they're a big amount of magma that exists sort of interstitially within a mush and is very rapidly extracted from that. And that's sort of a family of large eruptions that you see in arc environments and other places. So in that, and then there are models for that involving things like pumping a lot of gas through quickly and heating that up, something like that. So yeah, there are geometries where you might expect to have a big body that is not mobile, that you rapidly, and by that I mean decades to centuries, extract that liquid fraction from. And that would happen in the shallow crust, and that would produce, I mean, that is another form of magmatic differentiation too.
I guess this is just a follow-up question or a comment to something that was raised just a minute ago. I wonder, in terms of building a mechanical model that would have the lithosphere in it and that has some magma plumbing system to address these issues, right? What sets the spacing and so on. What are the main challenges right now? Because it seems to me it would be a good time to put things together, right? And people have looked, for example, at sort of bulk descriptions. What if you have elastic damage? Do you produce double island chains or not, as applied to hotspot chains? And we could combine those approaches, the bulk approaches, with some physical understanding of the magma system. And on the other hand, right, a lot of people have worked on two-phase flow, and then I'm not sure, it's probably not the same Keller, but Tobias Keller and a bunch of other people have built these fairly detailed mechanical models that could address some of the homogenization issues. So it seems to me, you know, that you could do quite a bit right now to answer these questions. Well, does the background stress field matter? Are we a little bit held back by the knowledge about the density and viscosity of the magmas?
I don't think so. I think that enough first order knowledge is there to give it a shot. We have a lot of constraints from the volcanic end, you know, to kind of tune or to see if we're going in the right direction. Yeah, I think it
seems like it is a good time to do that, right?
Yeah, I think it would be great. Yeah.
This is maybe a question better addressed to seismologists in the audience, but following up on the discussion about the absence of seismically identified shallow eruptible magma chambers, what about the deep crustal hot zones or MASH zones? Where beneath arcs can we see strong seismic evidence for those? Because that's another concept that's become strongly enshrined in the petrologic literature. And yet one of the puzzles when you go to exposed arc crustal sections is you see very little evidence for that. In fact, you see very little evidence for any kind of pre-existing rock.
I guess I'd take. I mean, some places you can see what is construed as evidence for that. Whether I don't know whether there really are a mash zone or not. I don't know. Yeah, it's true. And I don't know about the seismic imagery thing. I would be very interested to know that, because it is. You expect that to be a bigger target. I mean, it's deeper though, so. But then again, I guess beneath Mount St. Helens is. I don't quite understand what's going on down there.
I think maybe a
general perspective is they're not as easy to find as we might think they should be.
Yeah.
Even that thing beneath Mount St. Helens, it's the slowest thing around at Mount St. Helens. But it's not so slow that it requires a large amount of melt or anything to explain it. You could go a lot of different routes with crustal composition and try to explain it.
Yeah, right.
But it would, there's presumably some melt route that gets up to all those volcanoes, so the slowest thing around them looks like an attractive place, but that's not certain. So they don't seem terribly easy to find.
Yeah. Well, I mean, that's that would be interesting to explore, like try and put some thermal constraints on maybe how big they would be, and then say, is that something that would be evident or not? I mean, at Mount St. Helens doesn't seem like you're going to get a place that has more dense data coverage, so that would be the place to go.
Well, just to add on to that theme, we're talking about time. So a really good question then is how transient are the features that we're looking for? Because we need to know something about, I mean, there's some constraints from the thermal requirements that Adam alluded to in order to be able to melt the crust and things like that. And so, but if you get down to the minimum end of those and then say, well, what's the flux rate required and time integrated signal, and then you look at sort of what we say no at a better studied system like St. Helens about what comes out the top, I guess we could start to do some calculations about how transient could these things actually be. And so I think that's an important part of trying to understand it. I mean, at St. Helens and a lot of these places, we're talking about magma storage events leading up to eruption that are happening on months and years cycles, right? And so, how long is that sort of magma in the system or in one part of the system is a good question.
Yeah, I think that there is some evidence in the Kluchevskoy group in Kamchatka for an anomaly at that sort of depth that could be this sort of deep mash zone. It's also interesting from the geodetic point of view in that there, what we seem to observe is really rapid subsidence of a very broad area, which you can only get by having something coming from great depth. So it is perhaps that's also, it's a place with one of the highest magma fluxes on the planet, at least in terms of anything arc related.
Yeah.
So that may be one good example.
Okay, we're going to go to the last question, because this afternoon you're going to do synthetic tomography. And you will need to stock up on calories before you do synthetic tomography.
I hear the pizza is good.
So this is more of a comment too on exposed mash zones. Isn't the Famitinian basically supposed to be a mash zone?
That's the interpretation.
The Kohistan and Talkeetna arcs, exposed petrologic.
I'm not as familiar with those, but certainly the Famitinian, that is the interpretation, yeah. But even a place like the North Cascades has, one particular part looks a lot like a mash zone. Well, it's really confusing, so that's part of it. Rocks, we can get information over a very dramatic range of spatial scales, going from sort of volcanic provinces. This might be the whole arc or a segment of an individual arc. And then I'm not going to go through this in detail, but we can also get really valuable information by looking at the submicron or the micron domain in individual crystals. And to paraphrase Sorby, who I think in 1858 published the first paper that really described melt inclusions and flue inclusions. So melt inclusions are little bubbles of melt that are trapped in crystals that are very useful for reasons that I'll go into in a little bit. He basically said something like, I can't remember the exact words, but the size of something is really doesn't scale with its importance as a fact. So we can take inferences from very small domains and make important inferences about the way that volcanic systems work. But the study of volcanic rocks in arcs does cover a range of spatial scales, and just because I think, was it Doug or Jeff said this in their talk, sort of the scales that they feel like seismic studies get to. There is overlap here, but certainly we are getting information from much smaller scales because we can put our hands on samples than we get using geophysics. And is that good, bad? I don't know. I just put it up there.
Yeah, we don't do thin sections much.
That would be cool. All right, the upper plate. So this is sort of a texty. I try to avoid text in this talk because it never really gets me very far, but these are just sort of some central thoughts. Okay, the upper plate is important because that's where we get transformation from what is essentially an engine powered by man. All right, let's get started. Yeah. I look like I've put a lot of slides in. You can't see the displayer's view, but it's maybe a little too many. But the good news in that respect is I don't normally drink caffeinated coffee, and I just had some. So we'll be able to move along quicker. However, if it gets too fast, if someone could just yell out, breathe, occasionally. If I talk too quickly, I know I have a habit of doing that. Let me see, in 1992, I grew up in Eastern Australia, which is, even though there's a lot of volcanic rocks, there's no active volcanoes, so it's sort of volcanically challenged. Anyway, in 1992, I went on a holiday to Bali in Indonesia and was lucky enough to climb this volcano, which is Gunung Agung, which had actually erupted in the early 1960s and killed several thousand people. At the time, I didn't even know that, but it was really my first introduction to really dramatic volcanic topography. At the time, I was a PhD student at the Australian National University, but I was working in the Archean, so in a very different geologic terrain. And I didn't immediately throw myself on the ground in a blinding light and dedicate my career to volcanoes at that point. But I'm sure it had an effect in moving my research in that direction. And I think it has that effect on many other people. Just to introduce myself, my name is Adam Kent. If I haven't met you, I'm sorry. Hopefully I will in the next few weeks. Although this is my last day here until the last 2 weeks, so I hope to interact with many other people then. I'm a petrologist and geochemist. Rocks also give us a way to link different types of subduction zone research. Particularly, if we look at young volcanism, they give us a way to link with the geophysical snapshot we get of the current state of the Earth as it is now. But because rocks also go back in time and we can date them, we can also try and link those snapshots with sort of the deeper geological history. And Brandon showed some great forward modeling to try and do similar things. In many cases, those models can be sort of pegged to or calibrated in some way, and calibrated in a very loose sense, to using the geologic record, of which volcanic rocks in arcs are a big part. So for this talk, after consultation with Christy, this is we've seen lots of cartoons of subduction zones, and this is one of my favorites, a paper by Bob Stern back in the early 2000s. And from seeing the list, Bob is going to be here at some point, which is great because he probably knows more about, he's probably forgotten more about arcs than I know. It's sort of, you have to be humble when you talk to Bob. Not because he's a nice guy, but it's just clear he knows a lot. It's incredible. Anyway, so this is his cartoon. I'm not going to go through the details. So the point to make here is that I'm really just going to focus on this part, what I call the upper plate. So the upper crust that melts from the mantle, pass through on the way to the surface. Later, I think next week, Christy is going to talk about what happens in the mantle, so I'm going to largely avoid that, with one exception. And then just to sort of remind ourselves of the type of information we get from volcanic rocks and magmatic. So I use those tools to try and study magmatic systems. And I'm particularly interested in the interplay between magmatic processes and volcanic events, and I have projects going on in a few different places, some of them related to subduction zones, some of them not. I also run a lab, so I measure things. So as much as we try and avoid it, our research is often influenced by the toolkit we have available. And that's one of the things I do. Volcanic arcs, or the subduction zones that underlie them, we can define it as an arcuate chain of volcanoes that overlie a subduction zone, have been recognized for a long period of time. They're probably the main topographic feature that defines subduction zones, particularly subaerially. You could argue that maybe trenches are more dramatic. But it's clear from that, and it's been recognized for a long period of time, that there is a strong spatial correlation between volcanoes and subduction zones, and part of the picture of understanding subduction zones in their entirety is trying to understand the processes that lead to the formation of volcanic arcs and the magmatic systems that underlie them. So here's just a very nice example. You know, when you get onto the continents, volcanic arcs don't look very arcy, but in the oceans they often do. This is the Mariana Arc. And so there's the various topographic features, the trench, the arc front, there's a well-developed spreading center, and then there's this older Miocene part of the frontal arc that has been rifted off by seafloor spreading. So if we think about volcanoes and we think about the magmatic systems that underlie them and the type of opportunities they allow or opportunities they provide with research, in one sense, they're to me one of the two main places where subduction zone research interacts with broader societal interests, the other being earthquakes, obviously. And so a big part of trying, or a big part of the underpinning of trying to understand volcanic and magmatic activity on arcs is to try and link to the various issues which are important to human society. Volcanic hazards is an obvious one, but perhaps equally important is that almost all the copper, for instance, that powers our industrial society comes from porphyry copper deposits, which formed in subduction zones and volcanic arcs. Then there are other issues related to environmental health and climate. If we move more into research, the sort of stuff that many of us are interested in, there are also important insights we get into things like volcanic processes, magmatic processes, crustal structure. But also because, you know, volcanoes are really a gift to geochemists, because they take stuff that was produced deep in the earth and they bring it to the surface where we can put it in our mass spectrometers. So they beyond these sort of societal and crustal scale issues, they also give us a way to look at really deep fundamental geological questions, such as the formation of the continental crust, long-term evolution of the mantle and the deep earth. So, you know, really we get insight to a lot of different problems by looking at volcanic arcs. And I'm going to keep saying volcanic, and if someone here is more of a plutonic person, which means, you know, magmas that didn't get to the surface but got stuck somewhere in the crust, I apologize. I didn't really get too much into the plutonic story here. I'll get to a little bit, but when I say volcanic, I just mean all the magmatic rocks that are produced in subduction zones. And so volcanic